January 1, 1925 was the day when we discovered the universe. It was when Edwin Hubble's work showed that the Milky Way is not the only galaxy in the cosmos. This discovery set the stage for the expanding universe and, ultimately, an initial Big Bang. But while observing the distant galaxies, Hubble discovered a pattern. He noted that a galaxy's recessional velocity is proportional to its distance. This means that the farther a galaxy is, the faster it moves away from us. This law is known as Hubble's law. Although this relation appears simple, it contains one of the universe's biggest mysteries. It's the number that equates the two sides, the Hubble constant. But why is this constant so critical for cosmologists? What answers can we get by measuring it precisely? Finally, and most importantly, how have the recent observation from the Hubble Space Telescope confirmed that something's really wrong with our understanding of the universe? Over the years, researchers have tried to limit the value of the Hubble constant. Still, the results added more to the confusion every time rather than clearing things up, leading to a cosmology crisis. But before moving to this crisis, let's try to understand what the Hubble constant portrays in the physical sense. The Hubble constant establishes a direct relationship between a galaxy's recessional velocity and the distance to that particular galaxy. So if we measure this recessional velocity in terms of kilometer per second and take the distance between us and the galaxy in megaparsecs, it would clearly state the Hubble constant has units of kilometer per second (mpc). So, if the value of the Hubble constant is 70 kilometers per second (mpc), it would mean that for every megaparsecs of its distance, a galaxy will acquire an extra recessional velocity of 70 kilometers per second. Represented by Ho, the Hubble constant is a significant number in cosmology. It can help have an end-to-end test of our understanding of the universe, from the Big Bang to its final fate. The physical representation of Ho seems easy to comprehend. But if it is so easy, why is it so difficult to obtain a precise value of the Hubble constant? Why is it considered a notoriously tricky entity to calculate? The answer lies in the parameters involved to evaluate the same. To calculate the value of the Hubble constant observationally, we need two quantities, the recessional velocity of a galaxy and its distance from us. The recessional velocity can be measured by observing the wavelength shifts of spectral lines emitted by the object, known as the object's cosmological redshift. However, the second parameter, the distance, is comparatively problematic. One of the standard ways to measure distance to a galaxy is via observing the Cepheid variables residing in it. Like all other variables, stars, Cepheids progress through a complete cycle from maximum brightness to a minimum and then back to maximum again. A Cepheid's variability period is directly related to its luminosity. The longer the variability period, the more luminous the Cepheid is. Astronomers observe the Cepheids and compare their apparent brightness with their intrinsic brightness. Then, by measuring the difference between the observed and actual brightness, one can estimate their distance using the distance module's equation. In this way, Cepheid variables act like standard candles, and Edwin Hubble used these variables to measure the distance in the first place. However, before making calculations, the period-luminosity relationship has to be calibrated with nearby Cepheid variables, whose distance can be measured using the parallax method. This stepwise measurement of cosmic distance is called the cosmic distance ladder, and the problem is that the uncertainty compounds with each